Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. It's my pleasure to welcome Ranjit Jala. So many of you already know Ranjit pretty well. He's a professor at UC San Diego, and he's been doing a lot of really cool stuff on ensuring that the software we use is very reliable. So he'll tell you about some of the stuff he's done there.
Okay, thanks, Trishul. Hang on, let me just figure this out. This goes next, this points, but none of my hands would be free then. Okay, so I'm not going to tell you about why I do this because I'm at Microsoft Research now. So we're just going to cut to the chase. I work on tools that check properties of software. Okay, so let me just get started right away. And what I'm going to tell you about in this particular talk are, if I get time for it, two distinct lines of work that I've been working on over the last few years. One is on static safety verification. Okay, so how do you verify assertions that the programmer might put in their code? And the second is a scheme for dynamically checking liveness properties. It turns out that this doesn't point. It turns out that safety verification is very nice for somewhat simple low-level properties, but these algorithms don't really work when you want to enforce liveness. And so we developed a separate scheme which essentially uses a kind of random walk approach to find liveness bugs. So hopefully we'll get to talk about both of these things, but we shall see. Okay, so let me leap right into safety verification, and I'm going to give you a little bit of background. There's probably stuff that most of you are quite familiar with, but it'll just sort of set the stage for what comes in the future. Okay, so I'm going to pick a very canonical safety property, which is memory safety. So here's a very small program. It actually does something. I've forgotten what it does. Oh, it makes a copy of an array A and it copies it into an array B. It's not really relevant what exactly is going on. The key point is at this line over here, there's an access, where we're touching two arrays. We're touching the array B and another array A. And we would like to know that this access happens within bounds. This particular write happens within bounds. It's between 0 and the length of that particular array. And of course, as you all know, if you can't ensure these things, if it can be that this I is outside the bounds of the array, then various terrible things start to happen. Right? It allows bad guys to hijack your machine, etc., etc. Okay, so what I'm going to do is I'm going to use that as a kind of very simple example, and then we'll build on a more complicated example. And what I'm going to do is sort of outline the 3 steps in which I'm going to look at this problem of safety verification. Okay, so first, what I want to do is to very crisply formalize this notion of array bounds, okay, or array bounds checking, and sort of describe it as a very generic safety property. And then I'll show you how one builds algorithms to check those properties. So let's go back to that little program. So I have B of I is assigned A of J. And here's the rest of the program. I'm going to simplify various things, right? For example, what I'm going to do is I want to check at that point that the variable I is between 0 and n, where n is the length of the array B. Okay, so I'm just making very simplifying assumptions. And then to further simplify, it's very easy to see why I is greater than 0. It was initially 0, and then we keep bumping it up. This is weird. We should only have one of these. Okay, we keep bumping it up, so I'm going to drop that part of the conjunct. And then I'm going to throw out all this stuff about malloc and so on and so forth, just to keep this example very simple. Okay, so with all of this, we're down to this tiny little program. It has just 3 lines, 0, 1, 2, and at this point I have an assert that I want to prove. I want to ensure that at this particular point, the variable I is always less than n. Right? So this is something we're all very familiar with. How can I prove that this assert never fails? So now, let me show you how one goes about designing an algorithm. Again, this is something that most of you are going to be very familiar with. I just want to kind of get the ground rules straight, which is we're going to find invariants, right? It's a decades-old idea. And what is an invariant? Quite simply, it's a predicate that is guaranteed to hold at each particular program point. So in this particular example, the invariants are going to be of this form. I'm going to say that at program point 0, in general, I know whatever precondition is guaranteed before this program starts executing. In this case, let me assume that I don't know anything about what the program variables are. And so the only fact that I'm guaranteed is going to be true is the fact true? Okay, it's simple enough. At this particular point, if you stare at it for a bit, what you'll see is that whenever the program is at line 1, the sum of I and j is equal to n minus 1. Right? It's initially n minus 1. Every time around the loop you bump it up, you decrement. It's always going to be n minus 1. And now at this particular point, since I enter the loop, I know that the sum is equal to n minus 1 and j is greater than 0. Okay? And as a consequence of these two facts, of this invariant, I know that n is going to be greater than I. Right? Because the sum is equal to n minus 1, which is less than n, and j is greater than 0. So I must be less than n. Okay? So far, so good. Very well. So that particular invariant proves the assert. And so how do we prove these asserts? All we have to do is figure out appropriate program invariants at each program point. Okay? So many of you have been working on this problem for a while, so this should not come as a big surprise. So here's the approach that, here's a very sort of well-known approach. What we're going to do is, to figure out the asserts, we're going to use sort of, middle school algebra, which is we don't know what the invariants are at each point. So I'm going to introduce a variable, let me call it x sub I, which is going to represent the invariant at line I. Okay? So I have x0, x1, and x2 are the invariants at each of these 3 points. And next what I'm going to do is figure out what are the relationships that must hold between x0, x1, and x2 so that they are actually valid invariants and they suffice to prove this assertion. Okay? So please, at this point, I should have said nothing surprising, but you should stop me whenever. It will soon get slightly more complicated, I promise you. But please stop me whenever you get lost, okay? Or if there's something you don't follow, or if you think I'm lying. Okay, x0, x1, x2. So let's try and figure out what are the properties. What are the relationships that these guys satisfy? Okay, so as far as x0 is concerned, we know that x0 represents the invariant at line 0. I have no idea what the variables are at that point, what values they have. The initial values are arbitrary, so I'm just going to say that the invariant at x0 is true. It's just, it's the precondition that holds when the program starts executing, so it's just true. Very well. What happens after we just do this assignment, I is equal to 0? Well, at this particular point, when we're over here, I know that, well, true is true, and in addition, I is equal to 0, right? Because I just assigned I the value 0, so I is going to equal to 0. And then what's going to happen is I'm going to do this second assignment where j is assigned n minus 1. And so I end up at line 1 where I is equal to 0 and j is equal to n minus 1. Okay? Well, this is one execution that's led to line 1, and so the invariant at line 1 must hold. And so I end up with this particular relationship, that I equals 0 and j is equal to n minus 1 must imply the invariant at line 1. Okay, so this implication must hold. Let's move along. I'm at line 1 and I know the invariant x1 holds. When I get to line 2, what I know is that x1 is going to be true, and in addition, since I only come in when j is greater than 0, I have that at line 2 this fact holds. Okay, but I'm at line 2, and at line 2 the invariant x2 must hold, and therefore j equals greater than 0 and x1 must imply x2, right? That's yet another constraint. Now what happens at line 2? Well, we have this assertion, and so x2 must imply that I is less than n, right? Because we want that at this point I is between 0 and n. So the invariant at line 2 must imply I is less than n. And finally, when I jog down the body of the while, what I have is that at this point, I'm back, I know x2 is true, and then I'm going to increase I and I'm going to decrease j by 1. And so at this particular program point, what I'm going to know is x2 with the values of j and I replaced with some old values, I0 and j0. And the new values of I and j are respectively the old values plus 1 and the old value minus 1. Right? That's what I know at this particular program point. And here control flows back up to 1 because it's a loop. And so this formula over here must imply the invariant at line 1. And so I end up with another constraint like this. My machine has started chirping. I'm sorry. This is the screensaver. How does one mute this? Mute. Okay, very good. Okay, so far so good. So what are these invariants, x1 and x2? They're simply predicates that satisfy these 4 implications. Okay, no big shock so far. Okay, great. So now how are we going to infer these invariants? We're just going to solve for x1 and x2. Okay, and how are we going to solve for x1 and x2? Well, this is, sort of broadly speaking, one uses a technique called abstract interpretation. But I'm going to propose a specific form of abstract interpretation called lazy predicate abstraction, where what we're going to do is we're going to build a tree of executions over atomic predicates. Okay, let's not worry about where these predicates come from. So the nodes in this tree are going to correspond to these variables x1, x2, and the edges are going to correspond to these implications, each of these implication constraints. x1 implies x2. And what I'm going to do is I'm going to label each of the nodes in the tree with some conjunction of atomic predicates that have come out of somewhere. Okay, some kind of monkey, oracle, who knows what, has produced these atomic predicates. I plus j equals n minus 1, j is greater than 0. Great. So let me just show you how this works. So here are my 4 constraints down there. And the root of the tree is going to be one of these variables that has no left-hand side. So think of these arrows as a kind of child relationship. x0 doesn't have a parent, so that's x0 is going to be my root. And at each step, what I'm going to do is I'm going to pick one of these constraints, and I'm going to sort of unroll that constraint, thereby adding a child to this tree. Okay, so I start off with x0 as true, and I'm going to pick that particular constraint. And here's what I'm going to do. I have to figure out what predicates can I assign to x1, what invariant shall I assign to x1. And to find this out, I'm going to build on the work of many of you guys over here, which is to say I'm going to use an SMT solver. Okay, so I'm going to ask an SMT solver. I have this left-hand side, which says I is equal to 0 and j is equal to n minus 1 and x0, which is true. Right? So which of these facts can I prove? Which of these facts hold? And the SMT solver is going to say, I plus j is n minus 1. This implication is valid. So I'm going to say, OK, that's good. What about the next implication? The SMT solver is going to say, no, that implication is not valid. And so we're going to say, OK, I can label x1 with this fact, I plus j is equal to n minus 1. Okay? And we keep repeating this process. So now I'm going to focus on this particular constraint, j is greater than 0 and x1 implies x2. This time when I ask the SMT solver, it's going to say, yes, this predicate continues to hold. And this one also holds because of that conjunct over there. So I can label x2 with those two. Now I have the assertion down there, x2 implies I is less than n. Again, I'm going to ask the SMT solver this question, can you prove this implication? And the SMT solver is going to say, absolutely, I can prove it. Life is good. Okay, this implication is valid. I'm going to jog down, and here's my, that messy constraint. I'm going to ask it, which of these facts are true? I know that I plus j is equal to n minus 1 and j is greater than 0. Essentially, I bump up I and I decrement j. And so the SMT solver is going to be able to say, this fact continues to hold, but j is greater than 0 no longer. I can't say that for sure, because we just decremented j. OK, so I'm back, and I'm here with the label I plus j is equal to n minus 1. X1 has this label. And at this point, we can stop this process of unrolling, okay? Because essentially what's happened is I see exactly the same, I see the same node x1, and it has exactly the same label. So if I keep unrolling this tree, I'm just going to keep getting isomorphic copies of the stuff I've seen so far. So I can chop off the unrolling at that particular point. And in fact, at this point, I've found an assignment of formulas to x0, x1, and x2 that satisfy all of those constraints, okay? And so I found the invariance that I wanted to start with. Okay, so it's all good. I proved the assertion. Life is good. There was a small catch. Whoa. Where do the hang on. Oh no. Just when I said there's a small catch. All right. We're gonna need backup on this. Oh look, I managed to get it wedged in there. Okay. There's the small matter of where do you find these atoms? Where did this I plus j equals n minus 1 comes from? And I'm not going to tell you about the details of this. This is a kind of fairly well understood technology at this point. You start with no atoms, then you use counterexamples in an idea that was popularized right here. But there's a question about where exactly do you squeeze the atoms out from? And it turns out that you use a fancy logical technique called Craig interpolance. And you can get atoms like I plus j equals n minus 1 out completely automatically. Okay. So far, so good. Okay, so this is just a kind of brief background, a quick recap of how safety verification has worked in the past, which is to prove safety, you need to find invariants x0 and x1, x2, etc. at each program point. How do you find these invariants? You generate a bunch of these implication constraints, and then you solve these implication constraints using some sort of predicate abstraction. Yeah.
Clarification. What you showed the inference, is it very similar to the Houdini algorithm? Like if I think of Houdini
yes,
running it?
You can think of it as Houdini as well. Right? That's also actually Houdini is a kind of, you can think of it as a kind of Cartesian predicate abstraction. Okay. So this is all well and good, but this pretty much assumes that programming languages have not changed since the 1960s, because we're basically writing programs with integer valued variables and loops, and we're doing these little fidgety arithmetic operations. But there's a whole world beyond that. Okay, in particular, you have things like threads, you have asynchronous events, and then you really start getting into the modern era with things like higher order functions, polymorphism, generics, fancy data structures, trees, hash tables, maps, etc., and things like pointers, aliasing, mutation, and so on and so forth, right? And so how does one deal with all of these complications automatically? This is really the question that I've been focusing on for the last couple of years. And what I'm going to tell you about is some work that I did that looks at the question of polymorphism, higher order functions, and data structures. And let me tell you what the main idea is, and then I'm going to launch into a demo. Okay, so the outline for the rest of the talk is I'm going to give you a high-level idea of what's going on. Then I'm going to show you a demo that illustrates how this works in practice. And then I'll switch back into didactic mode, and I'll sort of pick up the pieces of what happened in the demo. Okay, and I'll go into some detail. Okay, so to motivate the approach that we've taken, let me first tell you what is the problem with data structures and higher order functions, etc., etc. Let me just use another seemingly very innocent-looking program. There's just a while loop, but we've thrown in some arrays. And this is actually a real program, by the way. This is the Knuth-Morris-Pratt string matching algorithm. Okay, but we're not going to worry with that. Let me just focus on this one line in this algorithm, where what we're doing is I'm using the contents of this array called table as I'm looking up the value of the position p minus 1, and this is going to be the next position p. So already you can see that I'm going to use this p in the next iteration of the loop. And so in order to prove that these array accesses happen within the bounds of the array, I'm going to have to reason about what the hell I put into the array in the first place, right? In particular, I'm going to need a universally quantified invariant that says something to the effect of every element of the table, every element that I store inside the array table exceeds minus 1. Okay, because, plus 1, whatever. This is why you have off by 1 errors. It is minus 1 actually, yes, by some. Oh, that's right, here's the plus 1. Exactly, okay, good. So somehow we're going to have to represent this invariant, and which I could write down in logic as for all I is greater than 0, less than table.length implies blah. But the trouble is that these kinds of universally quantified invariants get much worse when you have fancier data structures like lists and trees and such. For example, imagine that instead of storing it inside an array, I stored it inside some kind of linked list. So I would have to say things like, for all x that is reachable by transitively following the next pointer, starting from some root pointer, x.data is greater than minus 1. So again, you can devise fancy logics that represent these things. But with all respect to Leo and Nikolai, SMT solvers don't play very well with these for alls. Okay, it's a bit difficult to get them to deal with these kinds of universal formulas. And so what we've been trying to figure out is there a way that you can represent these invariants, these universally quantified facts, without using explicit quantifiers? Or to put another way, can you somehow use some different machinery to do the quantified reasoning? And the idea that we have is the following, is to essentially factor the invariant, to somehow split the invariant up into two parts. One is logic, the kind of simple predicates that SMT solvers like to reason about, and a type. Okay, so these are standard type systems, and to somehow combine logic and types in a way such that the logic can reason smoothly about individual cells in the structure, while the type system deals with the heavy lifting about quantifiers. Okay, so this is the goal. So let me just show you some examples. If I have something like for all I, blah, every element in the table is greater than minus 1, the way I might factor it into a logic and type is like so. I would say that the variable table has the type, it's an integer array, right? So the green part is just the pure type, integer array. But I have this little predicate that I attach with the integer that says it's an integer that's greater than minus 1. Okay? Let me show you what happens with the list. If I have for all x something, 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 I would just split this into a type that said the variable root is an integer list where each integer is greater than minus 1. Same thing. Okay? I've somehow factored the invariant. It's the same invariant, but I've split it into into the green part, which is a type, and the blue part, which is a logical predicate. And the key thing is that this logical predicate is a very simple predicate. It has none of that nastiness about the next star and the for all. Okay, and the idea is that the logic describes the individual structure, and so the theorem provers or SMT solvers, they can chew up those predicates very easily, while the type system is going to give us a very simple algorithm for dealing with structure, for doing this kind of quantified reasoning. Okay, and so at this point, what I want to do is swap out and show you, I just want to show you a demo of how this might work. So for many of you, even if you learn nothing else from this talk, you will learn about k-means clustering. So here's, let me just walk you through this particular program. Okay, so first let me just comment this out. Let's ignore that stuff, and let me just push this button because it'll generate a more color-coded version of that code. Oh, sweet. Okay, let's ignore all of those assertion may fails. Okay, for now. And now let me just step you through a program. Okay, so this program has two parts. In the first part, what I build is a toy MapReduce implementation. So a quick survey up. Is everyone here familiar with MapReduce, or shall I? You are or you're not? You are. Everyone is? Okay, so let me just step through it very fast. Okay, so it has 3 steps. Here, let's go through it backwards. So is everyone here familiar with F#? This is Microsoft. What's your excuse? Okay, so I don't have to explain what this means. I love this, that little pipeline operator. Okay, so okay, good. So this is think of it like a pipeline. It's a pipeline operator. So what it means is take x's and pipe it into this function. Take that result and pipe it into group, and pipe that result into these 3 functions. So this basically says take this input, pipe it through 1, take that output, pipe it through 2, take the third output, pipe it through 3.
No, it's the reverse Polish notation of applying it.
Yeah, I can show you the. This is what it is. It's a function that takes x and f, and it's just application backwards. So good. So at least you get. Okay. Okay. So what are the 3 steps of MapReduce? In the first step, what you do is you have a mapping function that takes every individual element and blows it out into a list of key value pairs. Oh, here we go. Okay, so you take each alpha and you blow it out into a list of B's and C's. Okay, so you get it. So these are keys and these are values. In the second step, what you do is you use these keys to group. Okay, so you gather for each B, you build a table that for each B finds what is the list of C's that was associated with that B in the first step. Okay, so this is step 1. This is step 2. And then in the third step, what you do is you do a reduce, which is essentially a fold over this C list. Okay, so you fold over the C list. Okay, so let me just show you the code. Okay, so the first one is, this is just completely trivial. I take f, my expansion function, and I apply it to every element in the list. Okay, quite straightforward. In the second step, I do this group by key. Okay, so this is my list of keys and values, and I make a little hash table, and then I just jog over each of the key value pairs. I look up, what is the list of values associated in the table with that key. If a list already exists, then return that list. Otherwise, just start off with the empty list and take whatever list I just computed and add this new value v to it. Right? So I'm just adding one more element, stuff it back in the table, and I iterate over all the keys and values. So at the end, I've clustered everything inside the hash table, and then I spit out that table. And then in the third step, which is this the reduce step, I do a fold, where what I do is I do a fold over the hash table. So for each, wait, why do I do a fold? Oh yes. So so for each key and list of values that's bound in the hash table, I do a fold where I associate that key with, I basically fold over, I use the reducing function f over all the values that are associated with that key. Okay. Now the key thing to notice is that for MapReduce to work, each key must be associated with a non-empty list of values. Right? This is it's like a non-null check. You don't have keys in this table that are associated with an empty list of values. And so you can use the first value as the starting function, as the starting element that you fold over. Okay? And so, if as long as the list is non-empty, I take the first element and I have the rest of the elements and I just do a fold. And this list should never be empty. So I have a little assertion there that says, heaven forbid that this should be an empty list. Okay? You should never associate a key with an empty list. So I have a little assert, etc., etc. And finally, the MapReduce sort of just stitches all of these steps together. I take x's, I first expand it into the key values, then I collapse the key values to get a hash table, and then I call my collapsing function with the reducing function to get whatever the result is. Okay, so far so good. Now what I would like to prove is that this assertion never fails. Okay, so that's one thing I would like to prove. But let's just keep the MapReduce in our heads. And let me just show you something you might do with the MapReduce. Okay, so one of the many popular things that one can do with MapReduce is something called k-means clustering. How many people here are familiar with k-means clustering? Just Trishul. Oh, 2, 3, very good. Some people are. Okay, so let me briefly, it's actually very simple. Let me, even I understand it. With k-means clustering, you have a bunch of points. Okay, that's awful. And you have a bunch of, at each step, it's a kind of iterative process. Okay, at each step, you have a bunch of centers. Okay, and in each step, what a point does is it just figures out what is the center that I'm nearest. Okay, so you have k centers, hence the name k-means. Each point figures out what is the center that I'm nearest. So it looks, oh, that's the distance of this center, these are the distances all. So each point says, oh, I'm near this guy, I'm near this guy, I'm near this guy, etc., etc. These points maybe say I'm near this guy, etc., etc., etc. And then, having figured this out, you compute a new center for this cluster, which is simply the addition of, it's the weighted sum of all the points that are in that particular cluster, right? And then you keep repeating this until you think you found good clusters. Okay? So one way you might do this with MapReduce is the following. Let me just show you how this works. It's this is one of the textbook examples of MapReduce. You can parallelize this step where each point tries to figure out which center it's near. Okay? And so I have a little mapping function called nearest. So imagine, it's all polymorphic, right? So there's k-means, my k-means function takes n, which is a number of iterations to do this. A distance function that takes 2 points and returns a float that says how far the points are. A plus function that I'm going to use to find the centroid, because I'm going to add up all the points and divide by the number of points in that cluster. Okay? I take in a list of points that I want to cluster, x's, and I take in a starting array of centers. Okay, so this array has, these are the k centers. And I'm going to, in each step, update the array. So how am I going to do this? So I have a little for loop for 0 through n. I take my points, and I call a MapReduce, where the mapping function simply finds out what is the nearest center, what's the nearest center for each point. Okay, so what nearest does is it returns, well, I'll show you what it does. It finds the nearest center, and the reduce step computes the centroid. Because once I figured out, so the center is essentially the key, right? This beta is the center, nearest center. So then I just cluster. So the ith center has these points in it, okay? And then I just do a fold. This fold computes the sum of all the points in the center, as well as the number of points in that center. And so then I can just update the centers by saying, for each, do a map, right? For each center I, x is going to represent the sum of all the points in the center. Sz is size, that represents how many points there are in the center. So just update the center array for the ith center with x divided by size. Okay, so far so good. How do we compute the nearest? Well, it's quite elementary. This by distance function, this array represents my current centers. And here's some arbitrary point x, right? This is the thing that gets parallelized across all the points. And so I just compute a distance array, which is a map. I just map over all my current centers the distance function. So this tells me what is, this is my distance to the first center, distance second center, third center, etc., etc. And then I call min index on this DA, which represents which is the index in the array that has the smallest value. So that's the nearest center, right? So min index is, I've deliberately written it in a very iterative style, so you don't accuse me of only working with pure functional programs. It looks pretty much like C, right? I have a min, which is, it's an imperative pointer. I initialize it with 0, and then I just loop over all the elements of the array for 0 through the length of the array. If the ith element of the array is less than the current minimum, then update the minimum to be I. So I'm just iterating over all the elements of the array, and in the end I return whatever the min reference refers to. So this computes the minimum. So min index of the array represents the nearest center, and this simply says return the point x itself as well as a count 1 that says I am 1. There's exactly 1 point, because then the reduce step is going to add up all these ones and is going to tell me how many points there are in each center. Okay? Okay, good. So we all understand how MapReduce works. So what could possibly go wrong? So here are several things that might well, this pesky assert might fail. Where have we gone? This pesky assertion might fail. So I would like to be sure that this assertion never fails. Let's keep going. Here I'm touching these arrays. No, wrong example. Here I'm reading this array a.I. This may not be within bounds. This may not be within bounds. What else might happen? Jog along. Right here I'm updating this. I'm updating this center.I. This may not be within bounds. And the thing I want to emphasize is that this is pretty much touching all of the things that software verification algorithms suck at. In the sense that, where's this I coming from? We got this I out by calling MapReduce. Okay, so we're calling this higher order function MapReduce with these two things, and it's spitting it out as a list of values after having put them inside some hash table where it did the grouping by key, etc., etc., etc. Right? So these are all things that have traditionally been rather tedious to deal with, and we need a very fancy logics to represent invariants like this. So now let me show you how one. So what is it? Okay, what I did is I switched off all the checking. And so this is all the possible places where assertions might fail. Line 50 is the non-null. These are all the various places where we touch arrays. Okay, all of those might fail. Actually, there's one more place where something might fail, which I don't know if you kept your eye on, was this divide by 0. How do I know that this size is not 0, right? I mean, you and I know it because we started off with 1 and then plus is just adding up the size. But still, how do I, I'm doing this fancy fold thing, how do I know that it's not going to? There can also be overflows, very good, which we have pointed on. Okay. So first, actually, one of the things I want to show you is how might I, actually there is, by the way, I don't know if anyone can spot this, but there is a bug in this in the sense that if I call k-means with certain inputs, I can cause this program to throw an array exception. Can anyone tell me what that input might be? This does not work for all arrays. Exactly, right? So if the array of centers is empty, then all hell can break loose. For example, this min over, just crazy stuff can happen, okay? And so what I would need is a nice way to specify a contract that says that you should only call this with, arrays that are non-empty. And I also want a contract, so notice that it's one of these things where I'm passing into k-means a division operation. So I want to say that I'm giving you this division, but for God's sake, don't call division with a non-zero, with 0. Right? So how would one specify this contract? It turns out that it's very convenient to do in this type-based style. So let me just quickly show you that before I blah, blah, blah. Okay, here we go. Let's ignore matrix multiply. So here's what it looks like. Is this Chrome? Drat, I should have used. Okay, so k-means takes n this plus blah, blah, blah. So notice, okay, so I can specify that the division operation, the second argument that I pass it must not be 0. Okay, so I can say div takes an alpha, some integer, and returns an alpha, but that integer must not be 0. And where did that array of centers go? Here we go. Okay, so I have to pass in a center array whose length is greater than 0. Okay, and then various good things will happen. Okay, so this is how I might specify a contract. But having done so, what is it that the user needs to do? Is to write down these little program fragments. These predicate fragments like I plus j equals n minus 1, but it's slightly more convenient. So let me just show you what some of these look like. So this just says you can use as a program fragment anything that looks like value. Remember that v that we had v greater than minus 1, so this is v. V is greater than or less than any other program variable that I just represent by an underscore. This says that you can also use as a program fragment something of the form v is less than array.length of any program array. Okay, so this can match with anything. And finally, to prove that that list assertion does not get violated, what I'm going to do is I'm going to define a notion of lengths for lists. Okay, so length is it's a recursive function that just says length of is x consec is 1 plus 0, and the empty list is 0. And so I'm going to throw in a little an atomic fragment that says you may also use in your invariance predicates of the form the length of some list is greater than 0 or greater than or equal to 0. Okay, so strictly greater than or greater than equal to. And you can make up whatever little fragments you like. Okay, so in this particular case, these are just the 3 fragments that I picked. And now I'm going to push this little button, and all of these warnings are going to go away. And I'll just show you why they go away. This is where, unfortunately, things start to get slightly ugly. But let me just show you what invariant it computes for the stuff that goes into this hash table. So check it out. So this hash table, T, it says that the elements in this hash table, it's a hash table of alpha and a list of values. Remember, this is the clustered thing, where that lists has the length of that list is greater than 0, strictly greater than 0. Of course, greater than 0 means it's also greater than or equal to 0, so you have this annoying fellow in there. But you have this, right? And because it can prove this about the hash table, when it does this folding, it knows that each of these v's, each of those lists is such that, is this readable? Unclear. This is not. I don't even know where to look. Well, this is basically the list, right? If you, it knows that each of these lists has length strictly greater than 0, and it knows that the empty list has length equal to 0, and so essentially this is dead code. This can never fire, right? Because that match never happens. What's that?
The green.
This one over here?
So where does it say that the length is non-zero?
It says it right here. Actually, it says it in 2 places.
I'm just curious to parse it. So it's a conjunction?
No, to parse it, I need to switch back and see what exactly the type of fold is. K, V, Zac. Okay, good. So the first argument to fold is a function that takes 3 arguments, right? Key, values, and ACK. And values is the thing where we want this non-empty invariant to hold. So let's just look at the type of fold over here. Come on, buddy. Okay, good. So 3 arguments, remember? First argument, which is the key, alpha. The second argument, which is values. And this is where it knows that it's a list whose length is strictly greater than 0.
And I see 3 predicates.
What's the third one?
True. Inside the set comprehension, there are 3 predicates.
Oh, so there's a conjunction.
There's a conjunction.
Yes.
And some subsume the others, but we don't care about
we just
that.
dump it all out.
Cool.
Ideally, we should do some minimization, but don't get me started. Okay? Right. Okay, so that's why this one checks out, right? That's why this assertion passes. Let's jog along and see what happens with k-means. Let's see what type we get for min index, because this one is quite easy. For min index, we see that we take as input some random array A, and the whose length is greater than 0, which is quite crucial, which comes out of the fact that we only call this function with arrays that are non-empty. And the output is a number that's greater than 0 and less than the length of A. That's what min index is. Yeah? I'm not showing it. I'm sorry. V is implicitly bound over here. You should read this as V colon int. I'm just trying to save real estate on this slide. It really is V colon int. Okay, let's see what type we get for nearest. For nearest, I get as input. Why is this mouse moving? Okay. I pass in some disk function, some center array, some point x. And the output that I get is a list of values. No, hang on. Oh, it's just some list. Oh, drat. It's suppressing the printout. It's a list of values that's greater than 0. It should actually say what that list is. But I switched it off. My apologies. This is useless. Unfortunately, user interface design is not my strong point. Isn't it nice that this is pretty fast? Great. Okay, now shield your eyes for a second because it may, this is why. Okay, so what I get is that the output is a list where each element in the list is greater than 0 and less than array.length of the center array. Okay, so it's a valid index. There's another thing actually that you get, which is that the second element in the list is, remember you actually get a tuple, right, of the point, which is alpha, and 1. And so instead of 1, what it says is it's a value that's greater than 0. Okay, and this is the thing that's going to accumulate when we add it up, and it's going to help us prove that the division doesn't crash. Let's keep going. Centroid is pretty simple. Centroid just says that it takes as input tuples where the second element is greater than 0, and in the output, the output tuple is also greater than 0. Okay? And so finally, when you stitch it all together, in this MapReduce, all of these accesses are within bounds. This particular, just a second, Nikolai, this I is between 0 and the length of center array, and this size is strictly greater than 0. Okay, wonder if we can actually look at it. Ooh, this is going to blow up, sorry. This is hideous. It's in there somewhere if you squint very hard. But let me take your question, yeah?
So you use, the example uses a hash table type, and in the annotation it looked like it's abstracted. Do you create a model for it, or does your analysis go into?
It doesn't look at, it only uses the type signature of hash tables. So in fact, in this particular case, I only use the type for MapReduce, which looks something like that. So I can describe how, I guess remains to be seen if I have time for that.
So I insert something to a hash table, and then when I MapReduce over it,
I don't even know that.
When I fold over
Yep.
so you have one place where you insert to the hash table,
yes.
Another place where you fold over.
Yes, yes.
And the values that are inserted to the hash table relate to the fold.
Yes.
And you get that just by the type signature?
Just from the type signature. That's just Hindley-Milner. It's, okay. Alpha in one place is pipes into the, the input in the second place. So it just ends up unifying.
Okay.
Yeah, so basically when the MapReduce implementation is being analyzed, it's being analyzed completely independent of all these clients. It has no idea about, as it can't. Okay? So now let me just swap back and show you, I think we have some time, right? We can, let me show you a bit about how exactly all of this really happened. I kind of wave my hands really fast. And in particular, what I want to do is I want to step through some of these features and how they get handled. Okay, so you have base types, you have collections, lists, etc., hash tables, closures, and generics. And I just want to show you how nicely the type system combines with all of that invariant machinery that I talked about at the start of the talk. Okay, so let's start off with base types. Okay, let's start off with base types. And let me just, so this is a snippet that was there. I wrote a for loop as a function. And the way the for loop works is it takes a lower bound L, an upper bound U, and a function f that is called at each step. And it's very simple. If L is less than U, then call f on L and follow that up by recursively calling f for with L plus 1 UF. Right? So I use this, you remember there was a for loop that jogged over the array to find the minimum element. Okay, now as far as the language is concerned, the type of this function f is just int arrow unit. Okay, this function f, it takes as input some integer L and returns as output a unit. Right? In each step, that's all it does. So how am I going to figure out what is this, this liquid type for f? What I'm going to do is I'm going to generate a little template. Okay, where I'm going to say, well, it's some special kind of integer. I don't know what kind, so I'm going to create a little variable just like we had before. Okay, a little purple x1, and I'm going to say integer arrow unit. And now what I'm going to do is I'm going to look at how f gets used. I'm just going to generate a bunch of subtyping constraints, and those are going to give me constraints on this x1. Okay, so let's see. The one place where f gets called is over here. Actually, I'm lying over here. I wonder if you'll figure out where. But is right here, where I call f with the argument L. Right? So let's see what really happens. So you can think of it as L flowing into the input of f. Right? This guy is the input of f. And so I end up with a subtyping constraint that looks like this. The value equals to L, that guy, flows into the input of f, which is this guy, right, x1. this particular flow happens under that branch, right, where L is less than U. And so I say, when L is less than U, this subtyping happens. And now this little subtyping constraint is actually an implication in disguise. Just like the implications we had before, it simply reduces to L is less than U and V is equal to L implies implies X1. Just like those invariants we had before, it's exactly the same thing. Okay? And so I can use exactly that same machinery with the atoms and what have you, which is what those little underscore things were. And I get that the liquid type of F is, when I solve out for X1, I get this conjunction, V is greater than L and less than U. Okay? If you think about it, this satisfies this particular implication. And I just plug it into that template, X1, and I get that the liquid type of F is, it only gets called with integers that are greater than L and less than U, and the output is unit. Yeah?
It can also have disjunctions like
It can have disjunctions, yes. Okay? And this is what allows me to deduce, by the way, that remember how we were computing the min index. If we just step back to the code for a second. If you look at how the for was, so check it out. Over here, when I was computing min index, this I is going to be between 0 and array.length, because this is what allows me to deduce that it's between L and U. Okay, so that was easy enough. Let's look at collections. Okay, so first let me look at, there's two parts one can look at collections. One is the actual contents of the collection. What did I put inside the list? And two is, what can I say about the list itself? How long is it? Things like that. Okay, so let's look first at structure, which is this business of length. So this is the grouping function. Remember where we clustered by the key, right? So this is the group function. And let me just focus on these two lines. I compute the current values associated with the key, and then I take my new value, which was V, and I add that, and I stuff it into the hash table. Okay, so that's what this looks like. Now here are some of the types. So as far as the language is concerned, the type of the hash table T is an alpha beta list hash table. So it maps a key alpha to a list of betas. And the value, the type of this variable V's is a list of betas, right? Which I'm going to then write back into the. So as before, I'm just going to generate templates. The hash table is a hash table of betas, beta list such that X1, and the variable V's is a list of betas such that X2, just as before. And now, notice that in this branch, this value flows into V's. Right? I look up the value of whatever is associated with key in the hash table T, and I flow it into V's. And so this yellow thing, whose type is this guy, right? This is the elements of the hash table. This flows into V's. And so I end up with a subtyping constraint like so. This left-hand side is a subtype of this right-hand side. So this is really the reasoning that happens with the hash table, which of course simplifies to X1 implies X2. Quite elementary. Yeah?
So can I refer to, when I'm specifying the predicates, X1, can I refer to the guys who are coming next to me? Like, can I say that the list is sorted or something?
You can, but that goes beyond the scope of this talk.
Okay.
You can, we can talk about that as well. Right. Okay, X1 is right, less than X2, great. Where was I? Oh, the other thing that flows into V's is the empty list, right? So this is an if then else, so both of these guys flow into V's. So the empty list simply, it looks like this. Remember, the empty list is a list whose length is equal to 0. So len v is equal to 0 is also a subtype of this guy, which simplifies down to this. Okay, so that's two more implication constraints. And finally, this guy over here gets written into the hash table, right? The hash, I call hash table.add with this. And so what I end up with is that this guy, v const v's, whose type is len v is equal to len v's plus 1, remember the type of the length function, okay, is a subtype of x1, which is the contents of the hash table. So I end up with a third subtyping constraint that looks like this, where v's has the type x2. And this simplifies down to yet another implication constraint, which is just this. When x2, take whatever you know about x2 and substitute the value variable v for v's, conjoin that with this fact, that must imply x1. More of these implication constraints. And now these get solved out to x1 is equal to len v is greater than 0, okay? And x2 is equal to len v is greater than or equal to 0 because of this pesky equals. And as a consequence, I can conclude that the hash table, when I plug the results back in, is a hash table of values where each list has length strictly greater than 0. Okay? Yeah?
How come you didn't include information about the conditional in the implications you generated?
I'm playing fast and loose all over. For example, let me ask you a simple, just to save real estate and just for simplicity, right? In reality, it's all there. It's like a blizzard of stuff. Let me just show you where I cheated. I'm surprised nobody caught me on this. Click, click, click. For example, over here, look at this. I said, I remember I put out this one constraint. I didn't even involve this plus. How can it be that this plus is not involved? Because if I put L minus 1, clearly this type would not hold. Right? I don't call it between L and U if I start decrementing the lower bound. So what happened? Did I cheat? No, actually, I just left out. There's another constraint because of the fact that long story. Suffice it to say I did it for clarity. Okay?
You also assume something about purity of F.
No, I don't actually.
So you
Because
don't
F
say-
is not pure in this case.
But in this example, you don't say anything about the post state after F is called.
Sorry, Wabi? Yes, I don't. So my type has no information about the post state. So in particular, remember the F we passed in had a pointer, had that min index that we were playing games with. The type tells me nothing about that. All it tells me is it just tells me what inputs F is called with. Okay, so I'm only refining that which is explicit in the type. If you want to talk about things like state mutation, you put it into the type. So you just, you use some sort of monad trickery, and you just bung it into the type. Okay, but here I don't care. F need not be pure. In fact, it is not pure in the example I showed you. Okay, click, 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 structure, grade, length, mumble. Let's just move along. Let me show you one more quick example.
One quick question.
Yes, yes?
So the one problem if you're going to infer basically contracts beyond just types is that your interfaces in your libraries that you're just implementing will show specific things about the implementation that is maybe too specific, right? And later you might want to change it.
Yeah.
And you're stuck with it.
Yeah.
So, do you have an idea about it? Or?
I don't, but frankly, that happens with types too. I mean, this is just a general problem with contracts. I know this happens with types because I'm in the middle of this right now. I'm doing a bunch of refactoring. There's some stuff in the type signature. I was like, oh no, I shouldn't have exposed this information because now there's all these other modules that use this information. And, well, you have to suck it up and just make the change. But no, I don't have it actually gets worse over here, right? Because you're exposing even more information about these invariants and so on. Yeah. So, I mean, this is like an API design question. And to be quite honest, I don't have a good answer.
Wouldn't it be better that you just force the programmer to write down the liquid type instead of...
Oh, for the interfaces, and I do, right? Because in this case, if you recall in the demo, for this, I expect that you will write down, I mean, if it's an open program, I want to allow modular verification, and so you can specify, there's another matrix multiply, but let's ignore that. Here's a signature for k-means that gets checked. So it's just like you take the, the MLI or you declare some function to be method to be public. So you would, for public methods, you could write down a signature if you wanted to. And then I would, check that the client,
Would you always be able to, if I give a more specific type, a liquid type, than the one you inferred, would you always be able to check, to infer that implication?
Yes, as long as the implementation is a subtype of the contract.
Okay.
It doesn't. In fact, in this particular case, notice the contract just says value is not equal to 0, but my implementation is stronger, right? It's actually value strictly greater than 0.
Yeah.
So that's fine. So the actual check is that the implementation is a subtype of the contract.
Okay.
Okay, it doesn't have to be exactly the same. Okay,
Isn't it a good idea for programmers to specify these liquid types? Because, rather than inferring them.
What a loaded question. Here's what I think. I think for certain functions, you should specify the types. For example, those interface functions. Okay? So for interface functions, it really makes software engineering sense to specify the types. You'd be a fool not to. But if you were to go back to this little MapReduce example, if I had to specify the types everywhere, I would just die. Because in addition to specifying the types for little piddly things like f4 and len and expand and blah, 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 each of these guys, one of the things that people miss out is that when you involve generics and polymorphism, you have to also tell me the type for each polymorphic instantiation point. Okay, so for example, at this place where I innocently say something like, this is the wrong example. Actually everywhere, right? Over here, I say min equals ref 0. I would have to specify a refinement that told me this is between, 0 is between, this value is between 0 and the length of the array A. So it's like, think of Java and all its verbosity. Think of Java or C# minus the nice var and local type inference, where every time you declare a list, you have to say, oh, it's a list of ints or a list of string. Now, in addition, you have to tell me what exactly, what is the logical predicate for each of these places, right? And polymorphism, once polymorphism slips into the language, it's everywhere. So this would just be, it would really inundate you. And so it's very, very useful to be able to infer these things. Otherwise, I think this stuff is useless, frankly. But at the same time, everything should not be, everything is not completely automatic, because honestly, this is an open program. I don't know how this is going to be called. So I want to say you should not call me with, with arrays that are of length equal to 0.
I've seen a lot of code in which whenever somebody declares a linked list, they say only insert connected connections or like open files in this linked list. Those seem like good places to actually put that.
Yeah, so at kind of top level global declarations, that's a very useful place to put in. But you don't want to have it put in everywhere, because then it's it gets lame and it just makes everything unreadable. Okay, maybe we should just, I could go on and on. Oh, let me just show you this one last example, then I'll stop, okay? So this is the function that computed the, for each point, this is the map step in the map reduce, right? It computes for each point the cell that it's, the center that it's nearest, and the point itself, comma 1, because we're going to add up those points. So now the output type, and I'm removing some parentheses for space, is int, this is an int, times, this is a beta, times an int list. And so I'm going to generate a template that looks like that. I'm just going to make up those x1, x2s. And now, the type of array.map is, so this is one of those things where I put into the specification of array.map, because it's a commonly used library function, that it takes a mapping function, an array x, and the output array has the same length as the input array x. Okay, that's what this says. And so as a consequence, the type of DA, this distance array, is that its length is equal to the center array, right? Because that's what I got from there. And now when I do min index of DA, its type is that it's between 0, the output value is between 0 and length of DA. I'm just going to plug in the type of min index that got inferred. And as a consequence, for this entire output, this whole value flows into the output of the function. I end up with a subtyping relation that looks like this. This is the actual concrete implementation type, right? Min index DA is a value that's greater than 0, less than len DA. X is a beta, and 1 is of type value equals 1. And I generate a list of these things, list. And the right-hand side is this template, which is the output type of this function. So I end up with this subtyping relationship, which again just reduces to these two implications. I get one implication for x1. This guy implies x1, and this guy implies x2. But I have this thing in the environment, that DA is of type, the length of DA is equal to the length of center array. So I end up with two implications that look like this. And again, I solve them out. So this is what I meant by the type system deals with the nasty quantification, because here I'm saying, for all elements in the list, etc., etc. Type system just says mumble A list less than B list means A less than B. And I end up with these two implications, and I get this as my output. Okay, that it's a list of values where the key, the center, is between 0 and the length of the center array, which is essential for proving the array bound safety when I update the centers, and that the position that holds whether or not it's, how many points are there inside that cluster is greater than 0, which is what proves the division safety. Let me just blah blah blah. Let me just very quickly cut to the end. So this is very nice demo, blah blah blah, generics. There were generics all over the place, and actually the high level bit is it's very simple. You have the type of MapReduce is this. ML instantiates alpha with alpha, beta with something, C with something, right, at each call site. This is, or ML or C#. When you have a polymorphic thing, you instantiate it with some concrete type. All we do is we just say, oh, you instantiate beta with integer. I'm going to instantiate it with integer such that x1. You instantiate C with a times int. I'm going to instantiate it with a times int such that x2. Okay? And then I just plug it back into the template. Same thing works again. You just grind down a bunch of subtyping, reduces to a bunch of implications, and you get back these nice types. And so the high-level bit is that with vanilla programs from the 60s, this is the style, right? You have these per program point invariants, and you generate these implication constraints, and you solve them. And in order to deal with these richer programming features, you just generalize things to involve types. You use the types to deal with the parts of the invariant that are tedious to reason about with theorem provers. So you end up with representing invariants in this kind of factored format. You end up with subtyping relations, which generalize the vanilla implications, but which crunch down into implications. And then the same sort of abstract interpretation machinery will give you the invariants. Let me just tell you about some of the things we've used this for. So right now, I described everything in terms of ML, but in recent work, we've actually made this work for C as well. So you take in the program together with assertions, and you take in those little atoms, those fragments with the underscores. And you get as output, either it says safe, all the types line up, as well as the types for you to view, or it'll say, I can't type check this particular operation, there's some type error on line 38, as well as the types. And actually, one of the nice things about this particular style, instead of the purely model checking approach, where you just say thumbs up or here's a counterexample, is even when you fail, even when the system can't prove whatever property you want, it tells you, the types actually tell you what it knows. So I can't tell you over here that X is between A and B, but I can tell you that it's greater than A. And so it's a good clue to figure out what's going wrong, or where you might made a mistake. We've thrown in at a bunch of fancy data structures. So this is actually Madan's question, how rich are these invariants? And it turns out they're really quite rich. So for example, we looked at the implementation of finite maps from the OCaml standard library. These are implemented as AVL trees. So these are height balanced trees. These are just all the grisly stuff you see in your sort of data structures class. You insert, rotation, rebalance, what have you. And we can represent and very rapidly infer things like the tree is always binary search ordered. So the root, all the keys to the left that are smaller are to the left, all the keys greater are to the right. That the tree is actually height balanced, and that you don't drop any keys. Okay, all the keys that are supposed to be in the map are in the map. Here's an even more fancy data structure. This is binary decision diagrams, which no doubt you're all familiar with. Yeah?
So those annotation chatter make yourself, I suppose.
The invariants?
Yes.
Yes. You have to tell it what you want, right? Yes. Okay,
this is infer those.
Yes. So BDD is it's an acyclic graph representation for Boolean formulas, and what you want to verify is that along each path, the variables are in strictly increasing order, right? So x1, and the child has to be greater than x1, need not be x2, something greater. And this actually uses some fancy hash table trickery to do this sharing. And still we can represent invariants like the variable ordering invariant. And we've thrown out a bunch of very complicated data structures, so beyond just things like array bounds checking. And the point of this is simply that this is a very expressive mechanism. It's not limited to array bounds checking. We've also recently applied this to C. So that was a fair bit of work, but it's still very preliminary. So the benchmarks are really quite small. And for C, we've just looked at spatial memory safety. That is, say, the absence of buffer overflows and null dereferences. And these are all tiny programs. But the interesting thing about the programs is that these were all things that were entirely beyond the scope of automated analysis before. And the reason they were beyond automated analysis is because all of these, like the MapReduce example, have key invariants flowing through data structures like arrays, linked lists, and sort of arbitrary DAGs. Okay, and the nice thing about this sort of hybrid type logic mechanism is that you can represent those invariants really in pretty much the same way as that MapReduce example that I showed you. But of course, this is really very preliminary. That's pretty much it. Let me stop now and let everybody go to lunch and take more questions. Thanks.
So if you have something that builds on the hash table, so you're interested in modular verification, and you have mutations. So suppose that you have some class, a radio class, that somehow uses a hash table.
Yes.
And the radio wants the hash table to have exactly five elements. Mm-hmm. And now it calls a routine in a library that parties with a hash table in some way.
That parties with a hash table? Okay.
It modifies the hash table in some way. How do you write the specification that you want it to be of length 5, and where does the error pop out? I mean, where do you check it?
These are both very good questions. Let's pick the first one first, because that I have an answer to. The way you would write it is pretty much the same thing that I showed you for list length. Okay, where so for list I wrote this recursive function. For hash tables, or in general, I'm looking for an eraser. Sorry. What you would do is, or actually like array.length for that matter. What we've gone, the way, let me just show you what really happens with array.length, right? When I have, the array is basically you have a get and a set, right? And so what I give the get method a type that says that you take in an array, and some index I. So this is the vanilla ML type, and I get as output an alpha, right? Now what I've done is I've gone inside the array module, and I've given it a liquid type that says array called x, let's just say x, and an integer which is some value v that's between 0 and the length of x, and I get as output an alpha. So to do your hash table thing, what I would do is I would define some notion of hash table size. Let's just say I have a hash table dot size or dot length or something like that. And then what I would do is, let's just call that module my hash, okay, or hash 5 or something. What I would do is I would say that that each of the hash tables inside that was created inside that module was v of type hash.t such that size of v is equal to 5 or less than 5, if you prefer. And I would give the get and the set methods. So I would give the get method, for example. It takes as input a hash table such a of this size and some key alpha, and it produces a beta. Right?
So that's the specification I want in the user of the hash table.
Yes.
But I want to use the.
Oh, you want to enforce this?
I want to use the standard implementation of hash tables.
Yes. Yeah. So let's do this.
Where do you propose that this one be written? In the user of the hash table?
So you have here's the standard library. Let's call it hash table. And let's say I have my restricted hash table implementation that uses this guy, right? And so let's call that hash 5 or something like that. You want to use the same implementation, but I would put the specification in the interface for hash 5. That's where I would put it.
So then do you have to re-verify the implementation?
Of hash table? No, I don't. Because the hash table,
so
I'm just going to use
it. That it's going to maintain that invariant that you've written on the board.
So this guy doesn't have to maintain that invariant, right? It's just tables that I create over here that have to maintain that invariant. You see what I'm saying?
Yes. So then where do you verify that?
I verify it. I verify that any client that uses hash 5 never adds, so whenever I have a client that, creates a hash5.t, that client, the size of all those t's is less than 5. And, for all I know, hash5.t also creates instances of hash5.t. It's not, maybe you add some other function. So I would have to maintain that invariant inside that as well. So I would check it. I would write a signature for the getters and setters that are implemented for hash5.t. Because they don't hold for arbitrary hash tables, right? They only hold for these guys, the special class of hash tables. And any calls made to those getters and setters inside this would be checked, and any calls made to the getters and setters by clients would also be checked against that interface. The other implementations inside this, they would use the bare hash tables. So for that, I wouldn't have this very stringent. I wouldn't even have this size criterion. Maybe I would just add to the set method something that says that I take as input a hash table and I produce as output a hash table whose size is the input size plus 1 or something to that effect. Okay?
But if I think about the actual implementation, that since the underlying hash table doesn't guarantee those properties, every wrapper that I introduce in hash 5 has to actually do a dynamic check. How does it know that the base implementation doesn't, screw it up?
Wait, I didn't follow this bit about the dynamic check. Why is there?
Well, you're saying the underlying hash table doesn't know about these constraints. So if those constraints are only enforced in hash 5, how do you know that when it calls the underlying operations in the hash implementation,
because
whatever properties you
there is something I'm using from the underlying hash, which is that every time I add a key, the size goes up by 1. You see what I'm saying? So I am using that. I'm just not using this business about it's less than 5 or less than whatever bound. But I am using the fact that the underlying hash correctly tracks the size of any given hash table. Does that make sense? So that bit of work is going to be done over here, but the extra invariant enforcement happens over here. Nikolai, look.
Abstraction of the whatever is stored in the hash table?
Yes, and that is in this size, in that hash dot size.
Yeah, but I mean, you probably also need some sort of set, right? Abstraction.
Yes, and you could even do that. In fact, we do even do that. When I mentioned this thing about the OCaml finite map, so when I said keys implement a set, that's what I meant. When you do add, one of the, so just like I showed you a list.length, you can write a list.contents. And you can write for a map, you can write a contents function. And so one of the things we check for map is that the add method, so add takes a map and an x, and it returns as output a new map whose contents are equal to the old map unioned with x. And the remove similarly takes, does a set minus and so on and so forth. So you could write all of these, and they're in the map implementation. Yeah.
But it is still conceivable that if somebody creates a subtype of a base type, you might have to go and re-verify and strengthen the invariance.
Absolutely. Because, for example, when I designed the hash, maybe I didn't care about this size business at all. So the original signature didn't contain any information. So the way to think about it is that the type signature is an abstraction of what the rest of the world cares about, this particular module. And if later I want more information, then I'm going to have to revisit the abstraction. You're absolutely right about that. So let me actually give you one of the weaknesses of this system, since you mentioned a very interesting point. Is one of the things I showed you is that MapReduce uses fold, right? And fold is actually wonderful because it packs a lot of information inside the type. But one piece of information it does not pack is how many times does the folding function get called when you have a list. That's just not there in the ML type. You could write your own version of fold that has that, but it's not there in the ML type. And so in some sense, I'm using the type as a kind of baseline abstraction that I'm adding more information to. But some information has already been thrown away. And you just have to live with that.